Hi, this is our project overviewing the Stokes theorem. The Stokes theorem is a theorem that tells us that if we know the circumference of a shape, we know what's also happening inside of the shape. So lines 1 through 15 tells us what is going about and what the program is going to be. Over here for lines 18 through 39, we can see that the code asks for the user to enter a radius for the circle. The radius controls the size of the boundary we are using. In Stokes' theorem, the circle is the loop we travel around, and the flat area inside the circle is the surface. For lines 41 through 72, the code chooses how many points to use for the calculation. Smaller circles need more points to stay accurate, and larger circles need fewer points so the program runs smoothly. This helps us make the math results more reliable. For lines 74 through 79, the user is given the option to change the number of points used. This allows us to improve accuracy if needed, especially when the error is too large. For lines 82 to 96, we are choosing the vector field. This part specifically allows us to choose one of the three vector fields. A vector field shows how something moves at every point. Each field spins a different way, which helps us test Stokes' theorem in multiple situations. For lines 103 and 152, we are defining the vector field and curl. The code defines the vector field and also defines its curl, which measures how much the field is rotating. The program also sets the theoretical answer we expect if Stokes' theorem works correctly. For lines 155 through 179, we are looking at the line integral calculation. It walks around the edge of the circle using angles and checks how much the vector field pushes in the direction of the path. All of these small values are added together to find out how much the field goes around the circle. For lines 182 to 211, we are calculating the surface integral. This program looks inside of the circle and breaks the surface into tiny pieces. It measures how much the vector field rotates in each piece and adds it all together. This represents the total rotation within the circle. For lines 214 to 238, we are printing out the line integral, the surface integral, and the theoretical value. This helps us compare all three of the numbers on one piece. And lines 241 and 264, we are checking for error. If the difference between the two integrals is small, the program confirms that the Stokes theorem is verified. If it's not, it suggests increasing the number of points. For 267 and 341, this part creates pictures. One picture shows where the vector field and the boundary circle. The other shows the results in the error. This helps us visually understand how the vector field moves and how the math works. For lines 344 through 372, the program suggests other radii to try. This encourages experimenting to see that the Stokes theorem works for many different sizes of circles. Overall, this code shows that the amount a vector field goes around a circle is equal to the total in rotation of the circle. By calculating both sides and comparing them, the program clearly demonstrates the Stokes theorem.